I'm Bart Jardine. I work at the University of Washington in Herbert Sorrow's lab. We do a lot of development of tools for metabolic modeling and chemical networks in general, and do a big focus on reproducibility and standards in the field. And we also work a lot with, I don't know if you know David Nickerson, so
Yeah.
we work with him on a few projects. So anyway, before we get started, let me share my screen one more time. I want to get advertising here. One moment. Just to let people know that our upcoming seminars are in December 11th with Dr. Jackie Snoop, and December 13th with Dr. Anna Niarakis. So just let everyone know about our two more seminars coming up in December. Okay, so I'd like to introduce to you everyone Dr. Rowan Cockett. He's founder and CEO of Curvenote, which is a publishing tool and more designed for society journals, and which is focused on building open source and community-built infrastructure and publishing tools to support the scientific community and hopefully bring more principles of open science, computation, and interactivity to this field. Okay, if you'd like to start.
Awesome. Thank you so much. Okay, so in 1675, Newton sent a letter to Robert Hooke saying, "If I have seen further, it is by standing on the shoulders of giants." And that, I think, is really the ethos of science, is building upon other people's work and ideas. And what is interesting about this is that Newton and Hooke were rivals, and Newton actually meant that as a sarcastic comment, a dig about Hooke's slight build. And this is an interesting tidbit, but it also sort of points to the dissonance between the collective and the individualistic enterprise of science. So these two goals are often not totally in harmony, and that sort of illustrates some of the difficulties in play, I think, in scientific enterprise. So between personal ambitions, collective goals of an entire community, and sort of the sort of ultimate societal, like broad societal impacts that scientific research can have. And so in these expanding circles of scientific discovery, there are questions to ask on how the work you are doing can be reused and shared with others, and also the sort of alignment of all of these incentives along the way. And so if we look forward from 1666 to another discovery about gravity 350 years later, this is the LIGO detector, which is listening for gravitational waves with precision lasers. And in 2016, the detector heard a faint chirp, which was gravitational waves from the collision of two black holes. And this work won the Nobel Prize in 2017 as the first observation of gravitational waves using sophisticated data collection, software processing, and a massive team to actually bring all of that work together. But if we look to how these are communicated, and sort of this is 350 years of innovation, and sort of the innovation here is about two columns. And so I think it's worth sort of thinking about what's next. And that's not just about sort of removing the PDF, but really about incorporating the entire process of science into how we communicate research. And so there are a lot of groups that are thinking about this, including this group. And one community that I'll highlight here is the Force 11 community, which stands for the Future of Research, Communication, and E-Scholarship. They've influenced and stewarded a lot of working groups over the past decade and a bit, including the FAIR data principles, which I'm sure everybody here has heard of, software citation principles, and quite a few others. And looking to their sort of original manifesto, which was written in 2011, they left some guidepost recommendations that I think really structure the space well that I sort of want to explore with you today. So thinking about how to add data, software, and workflows directly into the publication as first-class research objects. Thinking also about how we rethink the unit and form of scholarly publications, and it doesn't have to necessarily be that sort of that PDF and paper that's 10 to 50 pages long. And then really thinking about how we develop better tools and technologies that support the entire scholarly life cycle, not just sort of right at the end at sort of publication. And so I want to bring some of my own experiences in talking through these challenges and bringing some of these recommendations to life throughout my career. And my background is in geoscience and in environmental science. And so my first day of structural geology in undergrad, the instructor told us that structural geology was hard because it required 3D visualization skills that some, maybe even most of the class would struggle with. And what was sort of frustrating about that was that he was right, and the grades in the class showed this sort of clear bimodal distribution of students who just got it, and the rest of the class who were struggling to keep up. And as an undergrad student being introduced to 3D visualization tools in MATLAB, I was learning to program, and I was seeing that you could change the ways in which these were communicated. And so a learner could go in and sort of add beds to an interactive program and tilting events and folding events, and then add unconformities and dikes and faulting and more folding, and eventually get to something that is really complicated and be able to sort of change those events. And what these students are doing is actually interacting with software and visualizations all the way through. And so they're starting to interrogate these models and engage with these concepts in a totally different way. And this is something that resonated a lot with me, but also a lot with the students that were using these tools. And it was really pretty profound to get these sort of comments back from students who were struggling in these courses and saying that they owed a lot of their success in structural geology to these sorts of tools. And so that really hit a chord with students by sort of changing how we interact with these scientific ideas and infusing software and enhancing the learning experience and allowing students to discover ideas all on their own. And so those visualization tools that I built in undergrad went on to be used by more than 1 million geoscience students worldwide while I was starting my PhD. And my PhD was the intersection between hydrogeology, geophysics, and geology, and really trying to identify ways in which these disciplines could work together in a more quantitative way. And of course, in almost all fields, we were working with large-scale data and using software to process that data, creating optimization routines to come up with better models of the subsurface, using inverse theory to estimate parameters, and as well as write stories about those discoveries in scientific papers. And in all of this, I was building upon the work that my lab group had done over the years. And as tends to happen in a PhD program, my colleagues began to graduate. And as they graduated, I sort of realized that not all of the stuff that I was building upon from their work was there. The data wasn't actually stored. The software was on a local drive on their computer or unmaintainable by anybody else. And really all that we were left with at the end was this stories of the papers that were published, and really not a way to sort of build upon other people's work, even in a very close community such as a lab group. And so this sort of intersection between software, data, and story, these were some of the ideas that I was thinking about when I started Curvenote in 2019. And believing that science deserves better than a PDF and that it should be actually connected into the data and the software. And scientists really deserve better tools to communicate the work that incorporates software and data at the heart of that medium. And so Curvenote is two things. It's an editing tool that's online that is a what you see is what you get editor that you can sort of add citations to and have sort of a rich writing experience and be able to cross-reference things in comments, for example, to figures in the paper. And then it's also a way to integrate data software into those narratives in a very sort of integrated way. And so this example is Jupyter Lab running on the left, and then the Curvenote running on the right, and you hit Command Copy and Command Paste on the right-hand side, and you're actually bringing that sort of reproducible figure that remains interactive all the way through. And one of the things that we are doing at the moment is really focusing on the publishing aspects of this so that we can bring that reproducibility and interactivity and computational data all the way through to the final published artifacts. And so here we have a notebook rendered as an article. This is in partnership with the American Geophysical Union. And that notebook is now entirely machine readable. It works with the scholarly publishing system, adding sort of that rich scholarly metadata, as well as providing a rich and sort of beautiful reading experience that is actually connected to the data and the software. And so looking a little bit about the types of tools that we're building, in 2021, funded in part by the Sloan Foundation, Curvenote open sourced many of our tools to help reinforce the MIST to Markdown ecosystem. And MIST, which stands for Markedly Structured Text, is a markup language that can connect data and computation, as well as the specification and the tools, and sort of a diverse community around that actually supports those tools. And so out of this community, there's been sort of more than 14,000 books and tutorials created. And so it's a very widely used tool. It's the Markdown flavor that's used in about 13 to 15% of the active Python documentation community. Earlier this year, it joined Project Jupyter, or the Jupyter Foundation, and there are just a ton of contributors to this tool. And at the core of markedly structured text is that you can start with MIST Markdown or notebooks, and then use this tool to actually parse them. And what we're parsing is and presenting is actually structured data. So you're pulling out, you can see sort of all of the author information over here, but also all of the content of that's in a very, very structured way. And from that structured content, you can create websites, you can export to any sort of PDF template, for example, and you can also create journals. And so this is the Physiome journal, which we're working on with the Center for Biomedical Reproducibility. And this is produced directly in MIST, and you can have sort of rich listings of that hosted by Curvenote. And so that's a little bit about the MIST tool. I'm not going to go into too much of a tutorial in that tool today, but it's very easy to get started. You install the tool and then you type 4 characters on your command line. And if you have some sort of LaTeX document there, a Markdown file or a Jupyter notebook, it does its best to sort of get you up and running with an article rendering of that and all of that rich content. And so I'd like to come back a little bit to these sort of spheres of knowledge in science and how they connect and intersect, and comparing sort of the mediums of how we communicate these. And that is often, especially in science today, very, very disconnected. So in scientific publishing, I think we're really interested in this sort of connection between data and story. And so, but how we actually sort of show that in the way that we present knowledge for reading scientific knowledge this is a caricature of scientific publishing today of sort of a 2-column PDF that you're looking at on your phone that you can't read either column at the same time, and you're scrolling up and down, and there's a data table on its side. It's not connected to the software at all. And really the data and the story in this sense is completely disconnected. And that's how we experience science today. And really software is off completely to the side. And if we look to other disciplines about how things are connected, this is a business intelligence dashboard, and that is really focused on exploration of data through dynamic and connected charts. And that is really quite useful when the context is already well defined. But again, in these cases, the story, the narrative parts of this are really quite disconnected. And so what happens when we bring all of these together, and software and story together, and there are really intentional ways to do that, to create connections, both between people and ideas. And I think this is something that we experience in our day-to-day lives with, for example, like social media companies that really do know how to bring data, software, and story together and provide these sort of very powerful ways of connecting people and communities. And there's maybe other ways to think about connection when we're starting to bring software and story together. For example, how to connect with an idea in that sort of educational context where you're exploring, for example, harmonics, and you're exploring different waves, and because you're bringing that software and story so close together, it's really building up those concepts dynamically and interactively. And as you bring more data into stories, you can ask new questions. And so this is an example about the hottest day on record, and asks you to start with choosing a city or your city. And you can then ask the question, what is the hottest day where I am? And that sort of connection with a sense of place to you is really bringing these even closer together. And so I think this is a really interesting intersection between these sort of three ideas and sort of three spheres of how science is communicated and worked on. And that interplay between software data allows for exploration, and between software and story, it allows for these sort of new types of connection to ideas, to places, between communities. And what we know well from the scientific literature is that the integration between story and data is really the backbone of comprehension. And at the middle of this is learning and discovery. And as researchers are in this space, we are playing this game between research and publishing, and it's sort of this intricate dance supporting ways between sort of moving between these roles. It requires continuous tools to support that sort of choreography, and sort of between working towards a new idea and sharing those insights, communicating discoveries with colleagues and with the wider world. And when we look to sort of how scientific publishing is and sort of feels today, it's really, really far away from that. Sort of that well choreographed dance is not how it feels. And especially that's when it costs, when submitting to journals in terms of time, the cost is $230 million, was an estimate that was done earlier this year. And that's just to sort of reformat to specific journal requirements. And then jumping through the hoops of peer review and acceptance to journals takes 1 to 8 months at a 77% rejection rate. And at the end of it, we're left with sort of the static paywalled article. And that's sort of the best of our system right now. And it's static, it's not connected to the software and data, and it's really having this sort of legacy of print being so ingrained at the center of our mindset of science communication. And so between research and publishing, we have this manual, closed, and inaccessible system. And this is something that the types of tools that we are building at Curvenote and MIST are focused directly at this challenge, trying to move this into a more automated process and ensuring that the tools and practices and communities that we're building around these workflows are open, and striving to make them as easy as possible to everyday researchers. When we connect how we work to how we share, it is really powerful. So platforms like GitHub, for example, or Wikipedia, these allow working and sharing in the exact same place. And I'd like to draw an imperfect analogy to another discipline of knowledge work, which is software development. And so the process that software developers go through to create new software and products starts with requirements. It goes through some sort of design phase and then development phase, and then eventually releasing a product or a feature out to the world. And that's when you actually get feedback. And from that feedback is where you actually get your actual requirements. And this is called waterfall development, and this has actually gone quite out of favor in software development, because that idea that you might actually be working on the wrong thing potentially for many, many months. And what has come into favor is this idea of continuous development, where you're starting and planning and designing, you're going through the same types of things, but you're trying to go through this as fast as possible, releasing, monitoring, and sort of getting that feedback all the way back so that you can go through the cycle again. And what these continuous loops allow for is rapidly getting feedback so that you can test these ideas against reality and you actually build the right thing, the right product, or the right tool in this case. And comparing these methodologies for how we develop and release software has been really well studied. There's lots and lots of software companies out there and people who are very interested in improving sort of the organization and processes for software development. And one of these studies interviewed 36,000 professionals worldwide and grouped their teams based on their software delivery performance. And that was around how fast do they recover from incidents, how fast do they release a new feature, what practices do they use, and what is sort of most important in how those teams are organized. And specifically, these studies dig into and compare the speed of iteration as well as the robustness of those processes. And so in terms of speed, the low-performing teams to the high-performing teams were 46 times faster going through the cycle when comparing those organizational methodologies, so waterfall development to continuous development. So deploying software, for example, if you're deploying that monthly or yearly and comparing to a team that's going every day or multiple times a day, you can see that speed up of actually being able to get feedback and get more information really improves. And from a robustness standpoint, because there's this focus on automation to support continuous testing, continuous integration, and continuous deployment, the change failure rate actually goes down by 7 times. And so sort of much like riding a bicycle, some level of speed actually helps your ability to stay upright. And that is only true if the system is working and there's actually these sort of automated processes that are accessible to the researchers themselves. And today, again, there's this massive gulf between how we're working and how we're sharing in science that is really an impediment to moving in that direction. So when we're thinking about sort of the existential challenges that are facing humanity of climate change, pandemics, water security, these challenges demand from science that we improve the ways in which we work and share to really meet the moment, to improve the speed of iteration, the time it takes to build upon an idea to get to that next breakthrough, that next insight, that next innovation, and to know that that work is robust and reproducible because it is connected directly to the software and data that is powering it. And these, I think, the only point that I'm trying to bring with this analogy is that these are not incremental improvements. These are transformative changes that we can imagine by looking to some of these practices in other disciplines. And this analogy of continuous science is adopting language and concepts from continuous integration and continuous deployment. And of course, this isn't a one-to-one analogy. Research is totally different than releasing a product or tool. But I think this analogy gives us a tool to think through some of the mechanisms to support continuous processes through automation, rapid feedback, feedback on errors, feedback on sort of integrating into the scholarly ecosystem, and focusing on those small, rapid change sets to accelerate getting feedback from peers. And many of the tools that are being taught on improving documentation in the scientific ecosystem, pulling on sort of the experiences that we've had in the MIST Markdown community, I think can be directly applied to communicating and distributing science openly. And so for science, that sort of seamless choreographed dance between working and sharing maybe does look a little bit like this in terms of planning and collecting data and analyzing that, authoring some sort of thing that you're getting out to the world, and then really focusing on those automated tools to actually get that out in a professional way such that it can be reviewed by peers, published, refined, and then go through that process all again. And the pieces that are largely missing in today's world of science communication are focused on the automation. And automation is so critical because it enables iteration and versions and being able to improve that idea directly in place. And you can share it earlier, you can integrate software and data in a clear way to actually support reproducibility. And that automation also improves things like checking metadata or reproducibility directly, and improving the quality of the artifacts that you're sharing. So trying to support this sort of seamless choreographed dance between research and publishing, these connections are between working and sharing, and what allows you to get rapid feedback and really work towards that next idea. And so bringing together software, story, and data, and sort of trying to have continuous processes around that, we can get to publications maybe that in the future look a little bit more like this, where you can directly explore data while you're reading the publication, or you can press a power button and bring up computational resources and allow people to explore your methodologies, your data sets in seconds, rather than having to dig through supplemental materials, download that, understand your environment, and actually bring that up all by themselves. And this idea of frictionless reproducibility, that it's sort of that it's milliseconds away rather than minutes or hours or weeks away, that's at the core of reuse and being able to actually build upon other people's work and stand on the shoulders of giants. And at the center of all of this is learning and discovery. And so what if we are thinking about sort of open science as a lake of content that you can explore, and this sort of open science commons where you're hovering over a footnote, diving deeper into research, pulling out somebody else's figure and going all the way down into the data and the software that supports that work. And what if we integrated computational models directly into the way that we're communicating, having these models not just update the data, but also the text and narrative and how we communicate right in there.
Mm-hmm.
And then for connected processes and sort of this idea of continuous science and focusing on ideas of automation checks, that really requires new tools that focus on bringing your software data and narrative all together in new ways. And so, for example, going into a directory of notebooks and Markdown, typing misstart, you bring up a publication quality article that you can iterate on and improve directly as you're working. You're seeing the final version of your manuscript that you could actually share. And those tools are community driven, and they can be directly in the hands of researchers. And there can also be tools for checking and automation and testing. So in this case, typing Curvenote check, you can see all the tools that publishers run directly before you submit, or even while you are authoring the content. So checking things like metadata, references, editorial requirements like article length, or do you have a data ability statement or funding information? And I think as software developers. If folks are familiar with that sort of discipline, you really do know the difference between a repository that has linters or pre-commit hooks or automated tests and integration tasks. And those repositories give a lot of feedback on the standards like line lengths and those sorts of things before you are merging that. And you don't actually need to change that after the fact. And these tools for checking and automation can also be not command line based. So if you're dragging a manuscript in, those can actually be checked and give you what you see is what you get sort of experience, where you can go in and see all of those checks and then see a preview of your content that you're ready to merge. And this is, again, it's putting the researcher back in control of actually how their work is presented. So this is a Physiome article that has these sort of hover reference experiences directly in the way that, that the work is presented. And of course, we can also get PDF documents out. And so this is, again, an example from the Physiome journal, which is using Curvenote and MIST to run their community journal. And I think these sort of ideas are already at the heart of the Center for Reproducible Biomedical Modeling. And I think what we're trying to do is trying to extend that into much more automated ways where you can potentially check some of these things in a little bit faster and more automated way. So next, I'd like to go through 2 case studies. The first is a microscopy journal that Curvenote is working with. This is the Team 1 at Lawrence Berkeley National Lab in California. It's a 2-story high microscope that records at 120,000 frames per second and outputs data at 480 gigabits per second. And that is the same global upload rate to YouTube. And that is one camera, and that is being communicated in a journal. And so you have this sort of 1.5 terabyte data set that you might collect. And in an article, you give an overview, but you also need to show the details. So you can create figures with many panels. You're zooming into a specific area, and you have sort of these like very, very complex figures that you're creating. And so about a year ago, this is Colin, who's the editor-in-chief at a new journal by the Microscopy Society of America. He reached out to Curvenote with the goal of creating a new interactive journal that was possible of showcasing data and software that the microscopy community was creating. And so this is the Journal of Elemental Microscopy. So you can see that it has all sorts of that metadata available. And then you have your an abstract, but you can also dive into different figures and actually turn on those computational figures. And so this is looking at some of the tunings that the microscope is going to have to go through. And then you can actually explore some of what the scientists are doing to improve those that scanning electron microscope. And I think, and then everything behind the scenes is actually fully reproducible. And so the scientists are sharing the data that they're creating, all of the code that is all packaged up, and then directly accessible at a click of a button. And what was quite interesting, having gone through some of this publishing process over the last year, is that there's this sort of healthy push and pull between the iteration of the narrative and the software that was needed to actually support these results. And so during the course of the review of these articles, there was improvements in the reproducibility of the packages and ecosystems of scientific tools that were behind the published work. And that was actually supported in the peer review as this article was going through the process. And it's, I think, a chance for editors and peer reviewers to reinforce best practices of packaging, reproducibility, data standards, and software versioning as the work is actually being produced. And so very similar to the workflows that you might have seen in the Journal of Open Source Software. There is direct GitHub integration here, which runs those series of automated checks, ways to proof your work before it's published. And then you can actually see that sort of final publication as it's going through directly there. And then this picture of a zebrafish, it isn't a picture anymore. It's actually a real visualization of that 1.5 terabyte data set. And you can actually zoom all the way into it. You can interrogate that data and sort of change bounds and actually look at it in very different ways. And again, this is reinforcing data standards because you're interested in that end state of improving and including this in a publication. And so there's improvements in visualization tools, in data standards, and sort of the ways that scientists are interacting with those. This is Lindsay Hagee. She's a professor at UBC studying carbon capture and storage and geophysical methods for mineral exploration. And in her lab, she's trying to design for some of these incentives directly under her control with her team to improve the ways in which they approach the open sharing of data, software, and story, so that when someone graduates, the knowledge doesn't sort of just walk out the door, and we don't lose those connections between the critical aspects of science. And so that her next PhD students can actually build upon that work and not really just be left with sort of this uninspiring listicle of 100 PDFs to read. And so Lindsay wasn't satisfied with the status quo, and all that is left of that being sort of a CV with limited ability to tell her own research story in sort of a way, in a creative way that she wanted to. And throughout her work, her and her team are creating all sorts of interactive apps for visualizing results and interrogating ideas. They're creating textbooks and visualizations that are fully open and reproducible, and deploying those course materials to students to easily get them up and running and exploring concepts dynamically. And of course, also still publishing PDFs and journal articles. And many of those artifacts that she's working on and her lab group are working on really don't fit the mold of a journal article. They're too difficult to publish. There's interactive widgets that explain a concept, or textbooks or blogs or notebooks or ideas or presentations. And so those things that she's working on have such utility and value to her community. But they are interactive and they need reproducible software and data at the core of them. And so Curvenote's been working with Lindsay on new ways to communicate her work and providing them a way to show off their publications and research stories, and sort of those through lines of iterating on concepts and ideas over a decade. And many of that isn't really possible with the piecemeal disconnected journal ecosystem that doesn't allow you to attach and infuse computational work directly in the research artifacts. And so these are a few examples of the types of things that she's doing with these tools. Is she's publishing textbooks and notebooks and sort of bringing that full compendium of work, of sort of the work behind the work, and having control and creativity over the ways that she is communicating that. And that includes meeting notes and presentations and sort of mini conferences like the Symposium that they run, and ensuring all of that work is archived and discoverable. And because of these new interfaces for presenting her work that reinforce standards and reproducibility, that's changed the incentives that she has built into her own lab, and that those sort of archiving requirements that she's now encouraging in her lab groups now have an outlet to show off that reproducibility of notebooks and textbooks and notes that encourage standards and curating and archiving throughout the group. And those concepts of continuous science and connecting how we're working to how we're sharing, the research and publishing actually opens up totally new collaboration workflows. And this is like just a screenshot that she sent me. Is like, these were two of her grad students who were coming in because they discovered some of her work. And then eventually that actually comes into both of these people working as postdocs directly in her lab. And so practicing this continuous open science opens the door for collaboration and really growing the community around ideas. So going back to where we are today, innovation is not just about a fancy journal article with interactive widgets and going beyond the PDF. It's about connecting software, data, and story with a focus on learning and aligning work all the way through, from societal impact to collective understanding to personal ambition to change a field. From gravity to gravitational waves, each of these discoveries has been monumental. However, in the arc of history, it's not the current scientific theory that we celebrate, it's the scientific process we use to show how that theory can be improved. The ethos and the process of science must be aligned to how we publish and share, interactively, iteratively, incrementally, openly, transparently, and infused with data and software at its core. So imagine a future where Hooke and Newton were not rivals, but close collaborators, publishing their ideas faster, more openly, more iteratively. What discoveries would society have unlocked sooner? Thank you so much.
All right. Well, thank you very much. That is pretty cool. I like the way that things are integrated. I guess, is there any people have some comments or questions?
Yeah, I got a question. So you didn't dwell too much on the technical side, but how does this happen at the back end? Where's all this stuff stored? How is it maintained? I mean, is it all on GitHub or something?
Yeah, there's a heavy reliance on software workflows, and so if
where is it hosted? Where's all this? When I go to a paper, where is it stored?
It is on Curvenote's servers, and then we can back it up on Zenodo or other storage locations. And so that those are sort of the static artifacts. And then it also requires, if you have computation in there, a Docker container, essentially, that's actually capturing the software artifacts. And that is what we're using to capture that.
I mean, who builds those? Because most people have no idea how to build a Docker container.
So if you've used maybe tools like MyBinder before, where you can list, so this is quite a heavily used tool in the Jupyter ecosystem that takes.
I know Binder. Okay.
So that's exactly the techniques that we're using. And so if you have a requirements file, essentially, if you're working in Python, you can specify that, and that there's a tool called repo to Docker, which takes your software requirements and actually turns that into a Docker container. So you don't actually need to know those pieces.
I mean, it'd be useful to see an actual example going from, the research to the paper, and how much that entails, because that's what I have no idea about, is how much work it would involve. But at the moment, I just I happen to use LaTeX. I write my stuff in LaTeX, make it look nice, ship it off to the journal, and forget about it.
Yep.
Now and we've been taught to do that, but now this is a new way of doing things, and I have no idea how I'm supposed to do it.
Yeah, so the work for elemental microscopy is all completely open. It's all on GitHub, and so that is a community to look to. But
hold on. Then somebody has to be able to be GitHub savvy. Maybe your graduate student in your lab will be, but the PI won't.
Yeah, I think that's fair. These are very much sort of next generation tools, I think.
Yeah.
And so,
but it's worse than next generation. GitHub is not an easy platform to use, or Git is not an easy platform to use.
Yeah, I think that's fair. There are many millions of people who do use it. And so
I know. I mean, I know, how many commands do I know? 5, and I dared go outside those 5 for fear of wrecking the entire repo. So, and I'm pretty computer savvy. I mean, I still program. I've written all sorts of languages. I've worked in industry and done all sorts of things. But there's only so much somebody can know.
Yeah. So an example, one of the journals that we are doing this with is a high school student who, a high school journal, they didn't have any experience in command line tools, Git, Markdown, Mist, Curvenote.
I know these are all learnable. I can
Hey.
learn all these.
Yes, yeah.
But it's the bandwidth. It's the bandwidth. And high school students, to be honest with you, I got 2 of them. They really have nothing between their ears. So there's plenty of space to fill up with other stuff. So the problem is bandwidth. So
that's totally fair. I think there is a reliance on grad students who are very capable of doing these things.
Sure.
The point I wanted to make with the high school students is going from 0 to publishing an article interactively with reproducible work. They had an editor, their instructor, who was there to help them along the way, but that was a week of training. And so that's about the delta that is necessary from starting from 0 knowledge of these tools.
I mean, I would strive to make the workflows simpler and simpler and simpler to use. Because you won't get any massive take-up otherwise. I've seen these kinds of things come and go. I remember one many years, 20 years ago. People have been exploring this idea for a long time. And what's held them back is the activation energy for somebody with their current workflow to fit into this new workflow. It's too much.
Well, there's 30,000 tutorials and books that are like maybe arguing with that.
I know there's plenty out there. But I would recommend trying to make the workflow as simple as possible all the time. I know you can't do it overnight.
Yeah.
To get rid of any of the rough edges that hold people back.
The example with Physiome, for example, that is they are not yet integrating any computational models directly into that platform. That is solely a LaTeX submission, and then it is going fully through the process. And so that's actually much closer to how this works today. But it opens up the possibility of integrating out into the future.
That's a good idea.
Incremental. So exactly. So you don't actually have to take on all of that, but you can start to integrate data in a better way. There's better sort of automation and tooling around that.
Yeah, that would work.
Can you take, like, if someone has a lot of their stuff in a Python notebook and it has, the access to the models and the data, and you have your manuscript basically written there, is it pretty straightforward to put it into Curvenote or into the web publishing?
Yes.
Fairly low overhead, or
it is. I would recommend trying it. Say pip install mist md and then type mist and see what happens, and you'll probably get pretty close. And if you have a LaTeX document there, it'll show you that in a final form of that publication. If you have a notebook form, it'll just show up directly there as well.
Okay.
Who implements all the little gadgets, the widgets with the sliders and things?
So that very much is a next step to take. And in the elemental microscopy journal, as well as in Lindsay's lab, those folks do it themselves. And these use Jupyter widget ecosystem, which is a highly used ecosystem out there.
I'd use that. I mean, it's not trivial. It's easy to do trivial things, but then when you want to go beyond that, it starts getting more tricky. But you can do that. Yeah. The other thing, if you have live papers that are actually, running simulations or analysis, that's got to be run on some compute cluster somewhere. Who pays for that?
So in the journals that we're working for, those journals are covering those costs.
Okay.
There's also new developments called Jupyter Lite, which is running that computational kernel directly in the browser. And so that's client-side code. And so that's That doesn't do everything, but it does run like SciPy, Matplotlib, those
Yeah.
sorts of tools, and those can then be run directly in the browser at zero cost.
No, that's the direction we're taking actually. You know, so
Yeah. So if you're going in that direction with some of your
Yeah.
modeling tools that can be run
we are.
interactively, then that is
Yeah.
quite exciting from sort of an educational standpoint or tutorials.
We have it two now, actually. Bart developed one of them, and we have another one developed by a couple of other people. So both are interactive.
Yeah.
Okay.
And I guess the other one I was thinking of is back a while ago, people use R and RStudio for trying to get active papers. There's some support for integrating R and RStudio type markdown, or is it the same
Yes.
type of markdown?
It's very similar. We can integrate with Quarto, which is sort of the next generation of R Markdown by POSIT. And then if you have R code, we can also run that directly in Jupyter. And so the combination is sort of, it's like a little bit different syntax in some places, but it's pretty close.
Okay. All right. I guess, anybody else have any comments or questions? I guess we got a little bit smaller audience today than we had imagined, but it is recorded, so
That's good. Yeah,
so
hopefully
you
it can
can
go
still
out.
spread the
Yeah.
news. Spread it.
Yeah. And it's fun to talk to you afterwards as well.
Yeah, I'm surprised we have so few this time. I don't understand that. What happened there? I don't know. We normally get a lot more.
Yeah.
I don't think it's anything to do with you, Ron.
No. It's all good.
Something may have happened at our end.
If it was such a small presentation, I could have done a slightly more interactive talk and taking questions throughout the time. But
I mean, at some point, it would be worth perhaps another time next year to go through the mechanics of actually creating one of these papers.
Yeah, that sounds good. There's lots of tutorials and webinars that we've done that I could point you to if you're interested in. But I'm also happy to give a new one for folks on your side or targeted to either Physiome content or
that may be the way to do it.
Yeah, that'd be fun.
And what would it involve putting in some simulators? You do interactive simulation.
Yeah, that'd be cool.
Yeah.
Okay. Yeah, it's definitely where we want to get to with Physiome. So, yeah, we keep pushing in that direction, and the tools keep getting easier and easier to use. But they're definitely improving habit.
And the tutorials are getting longer and longer.
I think the tutorials get shorter and shorter because they're very focused. Just say.
I mean, I've done so much stuff in my time. I mean, things you have to go through and learn, and oh dear. I'm building an online textbook, for example, based on Read the Docs. That's a tough one. I mean, it's possible to do it. You can do it.
I will tell you that MIST is a lot easier than that.
Yeah, okay, that's worth looking at. I mean, I like to start. Read the Docs had some very nice book styles.
Yeah.
That we use.
Yeah, there's jupyterbook is probably the most used tool.
We tried that. That was a disaster.
Okay.
We tried it. Was it 2 years ago? We were going to write an interactive book for a journal. Well, we gave up in the end. I think it was mainly because they kept moving the goalpost. They kept breaking our stuff that we'd done. In the end, we just gave up.
Okay.
So maybe it's different now.
Yeah, the tooling has improved quite a bit, as I know Andre would.
And we were at 0.6 on jupyterbooks. But yeah, it was too much. Yeah,
well, give MIST MD a try and
I can have a look at MIST.
Reach out. Yeah,
I can have a look at MIST. Yeah, certainly.
Yeah, it should be. There's still some things, especially in the book context, in terms of continuous numbering. Across all pages.
I mean, a book. If you could do one could do a book with an interactive book.
Yeah.
So the book I'm downloading is static, but it'd be nice to have interactive elements.
Yeah, there's some cool stuff out there. We were
Yeah.
working with a folks who was doing both a static one that they were publishing, I think, with Cambridge. And it is like a 400-page book that they're using in MIST. And then it also has interactive tutorials. Like every document is a notebook going through various ways to do mechanics and robotics and sort of automation and planning, which is really, really cool.
With MIST, I mean, I have an awful lot of LaTeX text. Can that be converted?
It doesn't even have to be converted. You can leave it directly in LaTeX, and
nice.
MIST reads it directly.
Oh, that would be a huge advantage.
Yeah.
Yeah, that's one thing that's kept me back, actually. I mean, I got 5 textbooks. I don't know how many.
Yeah.
They're all in LaTeX.
Yeah.
Okay.
Okay. Anybody else again? Any more questions? We have a few more minutes if you want. No? Well, again, Rowan, thank you very much for the
Yeah, of course.
presentation.
Yeah.
It was good.
I'm
It's interesting.
looking forward to seeing the recording. If you're going to share that, and I can help promote it as well.
Yeah, we have a YouTube channel. We have
Awesome.
about over 99 videos on it now.
Oh wow. Okay.
Yeah.
Now hundreds. Put it over.
Yeah. Yeah, we'll send you the link if
Yeah.
Hunter hasn't.
Yeah.
Anyway.
Yeah.
Okay.
Awesome.
Thanks a lot.
Cool.
All right.
Thank you
very
so much.
Yeah.
Have a good rest of your day.
Yeah.
Yep.
you too.
Take
Bye
care.
now.
Bye bye.
Bye-bye.